Suppose we have a linear time invariant system with a happy transfer function capital HS, and we're going to input a function described by the Laplace transform big X of S, and as a result we're going to get out the Laplace transform of the output called big Y of S. Now suppose that we have a very particular input that we want to try, namely a cosine of frequency omega naught. But this is one of these instant on cosines. It starts at 0 and it's 0 before that. So you walk up to the signal generator and you flip it on, and when you flip on the signal generator, that's your t equals 0 point. So what will we need in this particular case? We'll have our transfer function times the Laplace transform of a cosine, which is s over s squared plus omega naught squared. Now let's think for a second about what the partial fraction expansion of y of s is going to look like. I'll have a bunch of terms associated with the various poles of h. So maybe I'll have a p1, and maybe I'll have a p2. They could be a whole bunch of things. They could be unique, or maybe some of the poles are repeated, and then you would have to deal with them the appropriate way. They might be real, they might be complex valued, whatever. As usual, I'm going to assume that all of our time domain functions are real. You can do appropriate extensions for complex valued time domain functions if you need to. And we go ... So however many of these we have. And then we'll have a couple of terms in the expansion having to do with the poles of the input. So I'll have an s minus j naught. I like to put the positive imaginary pole first, and then I'll have a s plus j omega naught for the negative imaginary pole. And you could put whatever letter you want here. I don't want to guess how far down in the alphabet we're going to go. How about let's put an alpha here? I don't think I've done that before. I just got the idea to do that just now. This might be a terrible idea. Oh, I need to remember that this one is going to have a complex conjugate. I could call it beta, but I know that these are going to be complex conjugate pairs because they are the coefficients of complex conjugate poles, and our time domain functions are real valued. All right, so let's use the residue method to figure out what alpha is. So alpha is going to be all of this stuff. It's going to be h of s, s over, and let me go ahead and write this out. I usually don't do this at this point in the course. Okay, so what do I multiply by here? I multiply by the root of the term that I'm finding the coefficient for, and that effectively cancels these out, and that's what we would usually think of as a cover-up method. I've got my h of s, I have my s sitting here in the numerator. Oh, I forgot I need to evaluate all of this at s equal j omega naught. Okay, so I'll have s over s plus j omega naught evaluated at s equal j omega naught. Okay, so I'm going to be evaluating my big H at j omega naught. I'll have a j omega naught over 2j omega naught, and so the j omega naughts cancel, and I wind up with big H evaluated at j omega naught divided by 2. Okay, so let's take this and plug this back into our partial fraction expansion. So I'll still have my terms associated with the system poles, whatever those are. And again, these could be repeated in various ways, in which case you'll have these kinds of things to the square or the cube or whatever you need to handle any repeated poles. So let's plug in what we found for alpha, which was big H j omega over 2. And now this is times s minus j omega naught. And then for my alpha star, I just need to put a little star on my big H of j omega. And I'll have s plus j omega naught, but now with the 2 down there in the denominator. So what's the inverse Laplace transform going to look like? Well, I'll have a bunch of terms associated with the system poles. Let me just write something like system pole terms. We'll come back and talk about those in a second. And here I'll have big H j omega, which I'll write in polar form. So I'm going to write the magnitude of b h j omega. Oh, and I forgot to put the naught on these. So there should be a naught here, and there should also be a naught sitting here. There you go. Times e to the j, this angle, big H, j omega naught. And this is all times e to the j omega naught t ut, which is what I get from taking the inverse transform. And oh, let me not forget there's a divided by 2 up here. And so the next term, of course, is going to be very similar. The magnitude is unchanged. I'll have e to the minus j, whatever that angle evaluated at that frequency going in was, times here now e to the minus j omega naught t ut. So y of t still has all of these system pole terms, as I called them. And now I can use the inverse Euler's formula to rewrite this whole mess here as a cosine, as we have done many, many times. So I'll have a big H j omega naught sitting out in front. Then I'll have cosine omega naught t plus the angle of big H j evaluated at this omega naught. That gives me a phase term times ut. Well, that's a really interesting result. So if we go back much earlier when we were talking about Fourier transforms and frequency response, remember if we had a linear time invariant system with a frequency response big H j omega, I could take a cosine and put that into the system, and what I would get out is a cosine of the same frequency, but it would be multiplied by the frequency response evaluated at omega naught. The cosine would have the same frequency coming out as what in, but the phase would change. So the only difference between what you see here and here is that ut. So as far as the effect of putting a cosine in that has a ut on it, that starts at a particular point, there's only two differences. One, the obvious one, is that the output sinusoid starts at a particular point, and we have these system pole terms sitting here. But the rest of the behavior is the same. The amplitude gets multiplied by the frequency response evaluated at omega naught, and the phase, what happens to the phase? Oh, you know what? I need to close the parenthesis there. Let me scoosh this over a bit in order to make room to put a parenthesis. Okay, there I put another parenthesis. Happy now? Hope you're happy. I'm happy. Anyway, you add the angle of the frequency response to the phase. So notice that if our system is BIBO stable, then these terms will decay to zero. They might have some t to the whatevers in them. They might have some polynomial type things in them like t to the 5 or whatever. They may have some sinusoids in them with various phases. But all of these are going to have an e to the minus whatever in them somewhere that will cause them to decay to zero, in which case we can say that these terms are transient. And that's in contrast with this everlasting sinusoid that we'll refer to as a steady state output, to contrast with the transient output. So we can use the ideas from frequency response that we developed in an earlier part of the course in our current context if the poles of the system function are all on the left-hand side. Now, so far this lecture, we've talked about transfer function analysis that assumes the initial conditions are zero. But if you want, you can evaluate the results of those initial conditions separately. And if your system is BIBO stable, whatever effects you get from those initial conditions, those are also going to fade over time. They'll also be transient. So your steady state output analysis is still useful. So we've made a lot of references to the fact that there's a lot of similarities between Laplace transforms and Fourier transforms. So we started with Fourier transforms as something that you could certainly apply to a function for all time. And for our purposes of discussion here, let's assume that we're only exploring functions that have support on the right-hand side, or they might have an impulse at zero, so there's zero for t less than 0. And we have said, hey, you know what? This looks a whole lot like the Laplace transform. And indeed, you can get the Fourier transform of a function by evaluating it at s equal j omega. But there's a huge caveat on this. This only works if the imaginary axis is in the region of convergence. Now, many moons ago, when I first introduced unilateral Laplace transforms, I made the claim that one of the reasons I wanted to stick with unilateral Laplace transforms and not deal with bilateral Laplace transforms is that bilateral Laplace transforms were a big pain because they forced us to deal with regions of convergence. Don't worry, this is only going to be dealing with regions of convergence a little bit. Basically, if you think about the Laplace plane, the Fourier transform arises from evaluating the Laplace transform on the imaginary axis. That's what the effect you get is from plugging in j omega for s. But that only works if the resulting integral actually sensibly converges to something finite. So for instance, if you wanted to find the Fourier transform of e to the minus at ut, you could take the Laplace transform, which would be 1 over s plus a, and you could plug in j omega for s and come up with 1 over s plus j omega. But this only works for a bigger than 0. One thing you can't do is say, try to find the Fourier transform of a unit step function by setting a equal to 0, because that wouldn't be in the region of convergence. If you wanted to try to write something like this, you're in for a world of hurt. So basically, you can find the Fourier transform of a function by taking its Laplace transform and plugging in s equal j omega if that Fourier transform was finite and well-defined to begin with. Now, you can write down something that's the Fourier transform of a unit step function, but you can't do it like this. You can't compute it directly. You have to justify it in the sense of it being a limit of something that, before it actually hits that full limit, is somewhat vaguely reasonable. And that's a very weird thing. The Fourier transform of the unit step function defined that way doesn't just blow up at the origin, it blows up in two completely different ways. And using it effectively requires a great deal of caution. So I don't like to show it. You can look it up if you want to know more about it. I recommend actually just not looking at it. It's too scary and weird. And using it requires all kinds of caution and can get you into trouble. And so we've said that the Fourier transform of an impulse response is a frequency response that we labeled big H j omega. And we've also said that the Laplace transform of an impulse response is a system function, big H of s. And so obviously in the same way that there's this link between the Laplace transform and the Fourier transform, there's a similar link between frequency responses and transfer functions, where you can in fact get the frequency response by evaluating the transfer function at j omega, but that's subject to the same kind of caveat. That imaginary axis needs to be in the region of convergence. So there are some textbooks that really like to just think about the Fourier transform as a special case of the Laplace transform, because if you look at it, well, it looks like that's the case. The Fourier transform is just this little tiny bit along the vertical axis. And those textbooks will usually start with the Laplace transforms and then later talk about Fourier transforms. I don't like that approach because you wind up wanting to talk about Fourier transforms for time functions that can go back to t equals minus infinity. And then if you're going to go the Laplace first route, you then need to talk about bilateral Laplace transforms and regions of convergence, and then deal with all of the complexities of regions of convergence all the way through, instead of this last-minute business here where I'm just talking about it in this lecture. But as I've explained before, it's not just my desire to avoid talking about two-sided Laplace transforms that makes me want to stay away from the Laplace first, Fourier second approach. With the Laplace transforms, you're going from the time domain, which just has one variable, to a complex domain that has two variables, a real part and imaginary part. And that leads, pun somewhat vaguely intended, to some complexities. So I like dealing with Fourier transforms first because you can think about time as a one variable thing, and frequency as a one variable thing. So you kind of have this parity between the domains. Now, obviously, because I've been talking about them for a long time now, Laplace transforms are incredibly useful. So there's sometimes we're thinking in this complex domain is worth the extra complexity.